All right, so to start off the complex projectile lecture, we're going to talk about what a complex projectile is or what I mean by it. So let's say, for instance, that we have a soccer ball sitting here on the ground, and the soccer ball is going to be kicked up into the air and take the path of a parabola, kind of something like this right here. And when a projectile is launched up into the air like this, it does take the path of a parabola, and that is symmetrical, right? So we could divide this in half and have two symmetrical sides to this parabola. All right, so I'm going to go ahead and draw the ball at multiple points on this path, and you can do the same. So you're right there, the very top. Where's the top? Probably right there. Ball's smaller there for some reason. That's okay. And then right here, and right here. And maybe I'll draw this one over. Bring it up a little higher. Okay, so you have something like that. It's not perfect, but it'll do. All right, so we have this soccer ball taking the path of a parabola. Let's draw its initial velocity, and here I'll use I don't know, maybe I'll stick with black here. Yeah, I'll stick with black here. All right, so we have the initial velocity that it's launched at, which is going to be, we'll say, it's going to look like this right here. And once again, it's launched horizontally and vertically. And we know that we can split that velocity up into an x component and a y component, right? And let's use different colors for these. Let's go with green for the x component. And let's go with red for the y component. So I'm saying that this is going to be VIY right here. And this green one is going to be VIX. Hopefully you can see that. It's not too hard to see with that bright green. This creates a 90-degree right triangle, which are right angles right there. Here we have the angle that this is launched at. This will be theta, right? You get the idea, just like we worked on before. Okay, so when this ball is in the air, because it's accelerating at 9.81, right? Because AY, it's only accelerating in the y direction. It is not accelerating right or left. The reason for this is that the ball has already left the person's foot. So without a force, it doesn't accelerate anymore. So meaning the ball doesn't know the foot isn't there anymore. It's not contacting the ball. So therefore there is no force and no acceleration right or left. But there is an acceleration in the y direction. And we know that that acceleration in the y direction is AY, it's equal to G. If if down is negative, then we would say negative G, right? Assuming down is negative. So I can make a note of that. Down is negative, up is positive. All right, so this is the acceleration the ball undergoes. Because of this, the ball is actually going to be accelerating downwards the whole time. But even though it's accelerating downwards on the upwards path of its motion, what's going to happen to the velocity? Well, the velocity is going to decrease, right? So this red component is going to decrease. But maybe before we draw that, we should talk about the x direction. The x direction has no acceleration. We said this before, that AX is equal to 0. And because there's no force right or left. So what this means is that VIX, if there's no acceleration, will not change the entire time. So at this point right here, I'm sure, how many dashes did I use? About 6 or 7. So at this point right here, the VIX is equal, or the x velocity is equal to VIX. It stays constant, right? So VX right here is still VIX. It's still the same length. It's still the same amount. Maybe it's 10 meters per second to the right. And right here, because there's no x acceleration, once again, it's 10 meters per second to the right. And we're seeing that VX, which is really still VIX, right? I could keep that I on there. It is still the same amount, has not changed the entire time. You can draw it right there. You can draw it right here. Whoops, I was trying to use dotted lines. All right, and then right here, right before it hits the ground. Because once it hits the ground, that's another force. And we said the only force here is gravity because it's a projectile, so this is right before it hits the ground. All right, so there we can see that Vx is staying constant the entire time due to the fact that Ax is equal to 0 meters per second squared. Now in the y direction, since we're accelerating downwards in the negative direction, this y velocity, right, is not going to stay VIY. So at this point right here, it's going to start to get smaller. I don't know if you can tell that's smaller, but it definitely is. And then at this point right here, it's going to get even smaller still. And then at this point right here, it's going to equal 0. And that's an important thing to realize, is that Vy at the top, so I'll call it Vy top, is equal to 0 meters per second. Why is this? Because the ball has to turn around and move in another direction, right? So right here, it's the largest it's going to be pointed up, then it's slightly smaller. Does that look smaller? Let me make it a little smaller still, so so that it's clear. Let's see here. I think I can do a little bit better. All right, that's definitely smaller. And then here, we can go even smaller still, right there. And so you can see that that y velocity is decreasing on the way up until it becomes 0 at the top. Then on the way down, since the acceleration is negative, it stopped at the top because it had to turn around, right? So it stopped going up at the top and now is going to start to move downwards. So now we're going to see this be Vy right here. This be Vy. And I don't want to make it as large. I got to be careful as it is down here. This is the largest it's going to be. All right. And so what you can see if I zoom out then is how the y velocity changes throughout this motion, right? Now, the total velocity is the vector addition head to tail black arrow that I'll draw here of all of these points. And so let me go ahead and draw that in. So we see Vi is right there. And a good question would be, well, does it stay the same? And the answer is no, right? In fact, this velocity right here, this total velocity right here, is going to be smaller than Vi. So I can call it just V. I'm not sure, you know, what number to give it. I don't even know if I should give it a name. Maybe I'll hold off on that because it's not going to be the same as, well, I guess I'll call it V. Whoops, hold on. What's up? All right, almost erasing everything. One move. All right, so, and you can see it's actually getting smaller, right? Notice how I connect that head to tail. And at all these points, there's the right angle is still there. And the angle, but theta is getting smaller, right? It's not as large as it was at the beginning. Now, notice this right here. How do I draw v right here? There's no vector to add vx to. So v has to equal vx. So therefore, if this is true, then what we're saying then, if v equals just vx, then this is the slowest the ball will be traveling at any point is at the top. Because think about that, right? V, the velocity of the ball, is equal to the vector sum of vx plus vy. And it's actually the largest is going to be at the very start. Notice that, right? Because the red vector is the largest it's going to be, the VIY. Vx doesn't change the whole time. So it's actually the largest, is the ball is moving the fastest it's going to move because it has the most velocity, or has the largest magnitude of velocity, total velocity, at the very bottom. And then it gets a little slower here because you're adding the smaller Vy, slower still, and the slowest it's going to be at the top where V just equals Vx. All right, and then right here, obviously it's going to start to get larger now. Notice when I add these head to tail, now it's pointing down and right. I don't like how this Vx is right here. I kind of want that over here. It makes it look a little neater. Just because I like having the hypotenuse vectors label right next to it. I don't want there to be any confusion over what vector is which. All right, and then right here, obviously the largest it's going to be. You might say, well, it doesn't look the largest. Well, that's because my crummy drawing. All right, so there you have it, right? The total velocity vectors of the ball throughout this parabola or this projectile motion, this complex projectile motion. You have the fact that the y velocity is decreasing on the way up, the fact that the ball stops at the top and then increases its y velocity in the negative direction on the way down because it's accelerating in the y direction at negative g the entire time. And then because the acceleration in the x direction is 0 the entire time, you see that the x velocity doesn't change, that Vix is equal to Vfx is equal to any of these Vx's the entire time. And the ball is moving the slowest total magnitude at the top and the fastest total magnitude at the start and the finish. So in terms of magnitude, what we're saying then, because of the symmetry of projectiles, is that Vi will equal Vf for magnitude. And this is very similar to if I was to throw a ball straight up in the air at 100 miles an hour. And the ball went straight up, came to a stop at the top, right? And then on the way down, I was to catch the ball. That without any wind or any air resistance, this Vf would equal negative 100 miles per hour. And the magnitudes though, right? The 100 would be symmetrical, would be the same. And we see that same kind of symmetry play out in these projectile problems where Vi would equal Vf, assuming that the symmetry of the projectile was allowed to happen, right? It was a flat surface, and this was it started at the very initial point and ends at the very end point right before it strikes the ground. That would be true. So I think that hopefully that helps make some sense of these problems, because we're going to analyze this and look at it and solve for some different numbers, but this is really what's going on. So hopefully that makes sense, and if not, I will come back to it and talk about it more during class. All right, so let's go ahead then. Let me see if I can go ahead and turn this. All right, so let's go ahead now and look at the complex projectile worksheet. Well, actually, no, let's look at the K formulas and then we'll look at the complex projectile worksheet. So just like we did last time, let me go ahead and flip this one more time. Let's split up. Let's talk about this motion up here in terms of K formulas. Or just in general, let's talk about what our K formulas look like. Because I think that this is also going to help make some sense of things. I think it's easier if we start with the X direction. So in the X direction, we have our 3K formulas, right? K1, which is VFX equals VIX plus AT. We have K2, which is delta X equals VIX times T plus 1/2 AX times T squared. And we have K3. VFX squared equals VIX squared plus 2A delta X. Should we also look at K4? Yeah, why not, right? Delta X is equal to 1/2 VFX plus VIX times T. All right. Okay. Okay, so let's go through and look at this. So we said last time that, and we just said a second ago, right, that, and I noticed I forgot my X here on this A right here. I apologize. Did I miss another one? I think I missed one down here too. We said that in the X direction, the acceleration is equal to 0. That projectiles don't accelerate left or right, assuming no wind or air resistance. If this is true, we can say then that AX is equal to 0, and this term right here becomes 0. So K1 simplifies into this, that VFX is equal to VIX. And that's important to realize, right? Because you might say, well, yeah, that's obvious because where you start at the very bottom and where you end at the very end, because of the symmetry, that would be true. But it says even more than that, right? Because you can pick any 2 points as final and initial. So really it says that any 2 points, the X velocity is going to be equal on the projectile's path, right? So maybe you picked, let me get my highlighter out. Maybe you picked, let's go with orange here. You picked this point as being initial, and you picked this point as being final. And even though they're not symmetrical, it's saying that the VIX, right, is equal to VFX. And so the VIX right here would be equal to the VFX right here. And that's true, right? The X velocities don't change throughout that projectile's path. Okay, so let's come back down here. So K1 isn't very useful in the X direction, right? Because it didn't really help us solve anything, right? So we probably won't be using that too much. All right, in K2, AX is equal to 0. This entire term becomes 0, and we're left with this formula. And we saw that this one was useful during the simple projectiles, right, where we could calculate delta X as the range, and that seems like a pretty useful formula. All right, let's go to K3. K3, once again, AX is equal to 0, and therefore this entire term right here, 2AX times delta X, is equal to 0. And this just proves that VFX squared VFX squared is equal to VIX squared. Well, okay, we already knew VFX equals VIX, so of course VFX squared is equal to VIX squared. That really doesn't help us much either. So K3 is really not that useful either. So far it looks like K2 is the only one that's been of any use. Let's look at K4. K4 says delta x equals 1/2 VFX plus VIX times t. Okay, so what this is really saying, right? If VFX and VIX are the same, right? Let's just call them VX since they're the same. Check this out, right? So we're saying 1/2 VX plus VX times t because they're the same. So I can then rewrite that as delta x equals 1/2 times 2 VX, right? Because what's 1 VX plus 1 VX, right? That would be 2 VX, okay? Times t, and you can see where I'm going with this, right? 2 times 1/2 is just means that these are going to cancel, right? Because 2/2 is just 1, and we can then write what's left as delta x equals Vx times t. And really, this is the same formula that we had just a second ago from K2. So K4 really doesn't give us much other than what we already knew from K2. All right, so this is the big takeaway, I would say, is K2. K4 was the same, except I didn't have VI there. Technically, I don't even need the I there because the X doesn't change throughout the entire motion, the velocity in the X direction. So what I'm saying is in the X direction, even though we have all 4 of these formulas right here, right, that all we really need to know or to use is just K2. And furthermore, we're not even using the entire K2. We're just using an abbreviated version of it right there. So the X direction is super simple to work in. Everyone usually likes working in it first. But the Y direction is really what we're going to need, right? Y direction determines time and time in the air. And I think I mentioned that yesterday, right? And I can write that down again. Y direction determines time in the air. And then also, what else did I want to say here? Oh, and this is the important thing before I start listing the Y direction formulas is don't forget, right? I'm going to have 2 sets of formulas here, and that what's the bridge between the X and the Y direction? What variable is not dependent upon direction, right? And that is time. So time is the bridge between directions. All right, good deal. Okay, so these are just some major points I just wanted to make. And okay, so let's go ahead and go back up here and talk about the Y direction. I may be able to fit all of this on in that column there. I'm not really sure, but it's worth a try, right? Why not? Okay, so in the Y direction, so here, AY is equal to G. And remember, it's only negative if you consider down to be negative. So that's important to realize. But most times, I think you probably are going to make that decision. The first formula, K1, we can say VFY. Once again, you can put the comma there if you like. If you don't want to, that's fine. I kind of go back and forth on it. Is equal to VIY plus AY times T. Notice that when we write these formulas, these K formulas, we don't mix the directions, right? To go between the directions, we use time, but we don't mix our X and Y variables. I can't tell you how many times I've graded a student's test, and they'll have the X formula for K2, and they'll be telling me AX is 9.81. It's like, no, that is not going to work. And then after that, the wrong answer follows, and so you don't want to do that. All right, K2 delta y, right? Everything's about y now, is equal to VIY times t plus 1/2 AY times t squared. Remember, only the t gets squared there. Okay, and in the simple projectile one, we were able to cancel off VIY as being 0. But now we can't do that, right? Because if we go back up to look at that soccer ball, VIY has a value now, right? It's this red component here, and we just don't know what it is unless we were given an angle and a VI, but we could find it. And so these formulas are actually going to be tougher now, and this is why we call these complex, because we don't have stuff canceling away that makes our life easier. Let's go ahead and get K3. K3 was VFY. I'm going to square that, is equal to VIY squared plus 2AY times delta y. All right, so once again, nothing there we can really simplify. Just got to roll with the formula, and then let's get K4 because we might need it. Delta y is equal to 1/2 VFY plus VIY. Doesn't matter which one you write first there. I probably write different ones first because you're just adding them together times t. Oh, something's, let's see, it's not wanting to write. Uh-oh. Hold on 1 second here. Oh, a little struggle for some reason. Maybe I'm going to pause it there. See why. Oh, I see. Never mind. The stylus, the tip of the stylus, sometimes it comes off because you can change the stylus tip. And anyways, if it unscrews, then it doesn't write. All right. Anyways, so that's what we have there, right? Okay. So in the y direction, our formulas actually look the worst they've ever looked, and but we're gonna have to use them, and it's not going to be too bad. All right. Anything I can add there in the y direction? Not really, right? Just reminding you that y direction determines the time in the air, which is kind of tough to think about. And time is the bridge between the directions. Okay, so I'm probably going to come back to that here in a second. Let me pause it real quick. All right, so I guess what I want to say about time being the or being determined by the y direction, because I think this is a misconception if you think of time being determined by the x direction, which is incorrect. Here's where I could see a student saying this, and I think at one point I thought this. So if you had, say, K2 in the x direction, right? We just talked about it a second ago. You then, and when I saw this formula, I think as a college student, I was like, well, it looks to me like time is determined by delta x. And what I couldn't see here, and that's this. Let's solve this for time. Once you solve this for time, you might say, well, I can make the projectile stay in the air longer by doing what, right? By having it land further away, right? I can just increase the top of this fraction, and that will increase the time in the air. But if I increase how far away it lands, right, to the right, then I have to increase this. And therefore, if I increase both by the same amount, do I change the time in the air? No. Let's look at another example of that. What if you say that I can increase the time in the air by making the bottom of this fraction smaller, right? That maybe you would try to have it go the same distance, but decrease the x velocity. But the problem with that is that's illogical, right? You can't have it go the same delta x with a smaller x velocity. If you make the x velocity smaller, what's delta x going to do? It's going to get smaller too. And therefore, the time in the air stays the same. So this is why the x direction doesn't determine the time in the air. The y direction does. Okay, so hopefully that makes sense. And you're not as confused as I was as a college student when I was trying to figure that out. And I was like, what? Mathematically, I was just like, looks to me like time in the air is based off delta x. I couldn't understand that relationship, so hopefully you get it. Okay, I think we're good. So we have a picture of projectile motion that's complex because it starts with an initial y velocity in addition to an initial x velocity. We see that Vx doesn't change. We see that Vy decreases on the way up, increases on the way down because acceleration points downward. We see the symmetry of a projectile. We're going to see that we can take this projectile and call whatever we want initial and whatever we want final. So we could, as long as initial happens before final. So I could refer, for instance, to the very top as initial and the very bottom as final. Or I could refer to the very bottom as being initial and the very top as final. So we have we can be flexible with that. And that's good because these formulas are more valuable that way because they can handle different situations and scenarios. We also see that the velocity at the top in the y direction is equal to 0. And that's also going to come in handy when we're down here solving problems. All right, so let's go ahead and look at one of these problems. Here we have a complex projectile. These are all just going to be just what we drew, which is a soccer ball launched off into a flat field or whatever, and so we don't have to worry about anything else like that. It's the same picture we drew up there. But that being the case, we still want to draw it because we want to draw our Vix and Viy. And notice they used the variables that they used here. They used V naught. This is really just Vi. And this is really just Vix. And this is really just Viy. So if you don't like the not symbol, you don't have to use it. But we're being asked to solve for part A, to solve for Vix, and part B, Viy, and part C, time to the highest point. Okay, that's going to be halfway, right? Time in the air, that's going to be the total time. And then the range, how far it traveled to the right, we'll say, because we're going to have these projectiles go up and right. So I'll go ahead and draw Vi. I'll use blue here. And I think this angle, they tell us, is 45 degrees. So maybe I should use black for that. This angle right here is theta. Okay, so then we can go ahead and label these, right? So this vector goes up and right. So its components are going to be a right and an up, and I'm going to draw them head to tail. And because one is y and one is x, we know that they create a 90-degree right triangle, and that V is going to be the hypotenuse. So I'm going to go ahead and make that right angle right here. Okay, and since it's a right triangle, we can go ahead and label, right? We want to solve for these. V is the hip, VIY is the opposite because it's across from theta, and VIX is what's left, so it's the adjacent, but it's also next to theta. Hip is across from 90. It's a good idea just to solve VIX and VIY. Plus they ask us to, but that's just a good habit to get into for any projectile problem, that you want to take this velocity, which they tell us is 100 meters per second. I'm just going to write that down right here, and split it into its x and y parts. So that's usually what we have to do to solve these problems, right? Okay, so because it's a 45-degree angle, we should get similar values for VIX and VIY. And so let's go ahead and solve for the opposite first, something in the y direction, and we're going to use sine for that. I would probably, if I was you, get a separate sheet of paper for this, because you can already see that we're running out of room. I'm going to drink of water, jeez. Opposite is VIY. The hip is VI. We can go ahead and rearrange that, multiply both sides by by VI. And we end up saying that VIY is equal to VI sine 45, which we could have subbed in for VI, and we probably should. So let me rewrite that one more time. VI is 100. All right, and grab my calculator here. Once again, make sure you're in degrees, as radians will give you the wrong answer. Sine 45, I think, is square root 2 over 2. So we end up getting 70.7. We'll go one more digit there. 70.71 meters per second for VIY. Is that what we were supposed to solve first? Apparently it was VIX. My bad. All right, that's okay. So that was part B we did first. All right, let's go do part A now. We'll do the same exact thing. If I run out of room here, that's okay. I'll just add a page in. So now we'll say we want to solve for the adjacent, so we do write the cosine formula. Notice I'm writing these out. It's just a good move. There's better AP teachers than me that recommend their students always do this, because otherwise they will lose points on the AP test for making stupid mistakes. So I know it's easy and you probably got them memorized and all that, but it's just a good idea to write them out every time. The hip is VI. Notice the hip is always just the total velocity, right? And it's always the largest side. So now we can go ahead and plug in numbers here. VIX we don't know, but we do know VI is 100. So VIX, multiply both sides by 100, is equal to 100 meters per second times the cosine of 45. Plug this in our calculator, and it should be exactly identical to 70.71. Yep. Okay, and there's our answer for part, what was that, part A? Yeah. Okay, good. Now, the next question they ask us is time to the highest. So to find the time up to the top, we are going to take advantage of the fact that we know something about the top, right? We know at the very top that the y velocity is equal to 0, right? We said this earlier. So if we know that that's the case, we can then call that the final y velocity, right? So we're going to call this initial, and we're going to call this final. And, whoops, I don't know what happened there. What is that doing? Let me try and write that again. Oh, I see. I'm writing it. Okay. There, now it's happy. All right. All right, so that's what we're going to do. So coming back down here, I think I have enough room here. So what K formula are we going to use, right? Well, let's think about what we know here. Let's just jot this down, right? We know VIY. And notice I went right for the Y direction because of what I know about the top. So that's kind of my thought process here, right? Is which direction to pick. And I picked Y direction because I know more in this direction, right? I don't know how far, I don't know delta X to the top. I don't know time to the top. I know VIX. So what I'm trying to say is this XK formula right here, I don't know delta X. I don't know to the top. I don't know T to the top. So all I know is VIX. So I have two unknowns and one equation. That's useless. So I have to look to the Y direction. And I always kind of like going for K1 first because it seems like it's the easiest one. And I think K1 is going to be right here, right? Because we know VFY is 0 at the top. We know VIY, we just solved for it. It's that 70.71. We know AY is negative 9.81 because I'm going to call down negative, and we can solve for time. So notice what we're doing here, right? That T becomes the value based on where we picked final and initial, right? It becomes the time period between the two. And then that's important to see. So this is going to be T top, not T total for this equation. All right, so let me go ahead and write that down here. So I'm picking Y direction because I don't know enough about X direction. And if you pick the wrong direction, that's fine. You'll just get stumped and then try the other direction. That is totally okay, and that happens to me, and that's no big deal. So don't feel like, oh, I got to pick the right direction the first time. No, it's not what I'm saying. All right, so this is what we have here, right? This is K1. If you want parentheses there, that's fine. VFY is at the top, right? So final is at the, so this is going to be, so what I'm saying is, and I already said it a second ago, but I'm going to say it again because I like to repeat myself, and I feel like that it helps people learn. It might not. I think it just ticks off some people, but I don't know. I'm used to kids at tennis practice not listening to me, and so I say things 7 times, and well, I think I got that from, I actually taught freshman bio for 5 years, and so yeah, I'm used to kids with no attention spans not listening. So all right. Anyways, VFY at the top is 0. VIY is that 70.71 that we solved for. Notice it's positive because it's going upwards. And AY is going to be negative because it's downwards. And the time to the top is what we're going to solve for. If you want to write T top here instead of just T, you can. Sometimes I do that. Maybe I'll do it this time, but you don't have to. Feel free to just write T. Just realize, though, it is T to the top. All right, so now what are we going to do? What's our math move? Let's just add negative 70.71 to both sides. Kick that over here. I'm writing too large here, and I'm going to run out of room. All right, divide both sides by negative 9.81. Get rid of those negative signs, and we'll see T top is equal to what? About 7. Let me see. Divided by 1.81, 7.21. Units are seconds. And that should make sense on the units, right? Because, let me highlight this first. Why should that make sense on the units? Because if you think about it, we had meters per second, right, divided by meters per second squared. So when you have a fraction inside your fraction, you have to flip and multiply by the reciprocal. And the top fraction, that's for the bottom fraction. The top fraction, the seconds gets to move to the bottom. So what I'm saying is with the top fraction, it just becomes this, right? Meters per second. The seconds goes to the bottom, meters stays on top. This bottom fraction, meters per second squared, this guy right here needs to be flipped and multiplied by the reciprocal. So we can now see meters cancel. One of the seconds cancels that, and we're left with just seconds. All right. And that's what we got. Okay. Good. All right. Time in the air. There's a couple ways to do this, right? One, you can just say, well, symmetry of projectiles, right? And that's probably the easiest one. You can say, well, the time to the top was 7.21. So the total time in the air, it has to equal, let's say T total is equal to 2 times T top, which is going to equal 2 times 7.21? Yeah, 7.21 seconds, which is equal to 14.42 seconds. All right, and that's going to be our T total. And that might feel a little bit like cheating, but it works. If you don't like that and you're like, well, can't we use the K formula for that? Yeah, of course. Let's see. Let me add a page in here because I'm kind of running out of room. I think I'm going to add it down here, though. Let's see. Okay. So how would that look? Well, so if you used a K formula there and you wanted to, let me see. So you wanted to call, well, there's a couple ways you could do it. Let's say you did it this way. Let's say you wanted to call this the initial, right? The very initial. And this the very final. And you wanted to know T total, right? Okay. Let me think about that. What would be the best way to do that? Well, let's look at our Y direction formulas, right? Can we use K1? We could, but we'd have to rely on the fact that VFY and VY are symmetrical, right? That VFY would equal the negative value of VIY. So that would be a negative 70.71. So that would work. If we use K2, could we do that? It's worth a try. I don't know. Let's give it a shot, right? So if we solve for K1, let's start there. And we said VFY equals VIY times T plus, whoops, I'm writing K2. If we did this, what I was trying to say is this. We'd have negative 70.71 because in the final it's going to be pointed down, the Y velocity. And in the initial it's pointed this way. And we would have negative 9.81 times T total. Kick this over to the other side. We get negative, what is that, 141 point. It's getting too late. Can I do that in my head right now? Just get my calculator and do it. 141.42 is equal to negative 9.81. Divide both sides by negative 9.81. You get 14.42. So there's one way to do it. Another way, K2, delta y. Can we say delta y though? Yeah, we can, right? Okay. Let's try this. I'm not sure if it's going to work, but it's kind of interesting to give it a shot. And then after that, we'll probably just move on because I don't want to be here all day, and I don't think this is as interesting as I think it is to you guys. All right, so delta y between the very beginning and very top is actually 0, right? Because we're talking about this, right? Here's the initial, here's the final. So there's no change in y, right? Because we don't care about what happened in between. We just care about the difference between this initial point and this final point, and there isn't any. So that's got to be 0. VI, this is VIY, by the way. Let's go ahead and write the rest of it then. So we're saying 0 is equal to 70.71 meters per second times t total plus 1/2 times negative 9.81 times t total squared. Ooh, gross. All right, looks kind of nasty, right? Something we can do here is that we can divide both sides by t total, right? Whatever you do to one side, you can do to the other side. And you could also think of it as factoring out a t total and then setting it equal to 0 or something along those lines. But I think this is maybe the best way to think of it. So if we divide both sides by t total, of course, 0 divided by t total doesn't change anything, but we end up getting this, right? 0 equals 70.71 meters per second minus, right? Because it's plus 1/2 negative. So minus half of 9.81 is 4.905 meters per second squared times t total. And we notice we got rid of, if you check that out, right, we got rid of that and then one of these. So we're left with just one of those there. Okay, so look at that. Check that out, right? That looks like it should work. So we'll kick the 70 over here. Divide by negative 4.905 meters per second squared, if I can write well enough. And set that equal to t total. Type that in the calculator, and that should be right. All right. Yeah, 14.42. So what I wanted to say here is do it the easiest way, obviously, but I'm just showing you that these formulas are pretty flexible and they can handle what you throw at them. So, yeah, and there's multiple ways to do it. You didn't have to know the symmetry of projectiles, right? We didn't use that in this K2 the way I solved it right here. I didn't, at no point was I like, oh, because of symmetry, right? So I didn't rely on that knowledge. All right, good. So let's get the last part here, the range, and then we'll be done. So the range is going to come from is delta x, right? So finally, you're like, oh, it seems like all we do is use the y formulas, and I guess in a way, you know, you've kind of been right up to this point if that's what you're thinking. What the heck did I just do? What is? Oh, this is starting to mess up. I feel like let me check what I just did there. I'm not sure. I think this thing sometimes starts to struggle a little bit if I do too much with it, or I don't know. Sometimes it just screws up. Like I don't know why the highlighting all of a sudden dropped down here. All right, whatever. I'm just gonna keep going. All right, so now we're gonna look at the x direction, and since we want to know the range, the total change in x position, it makes sense to use K2 in the x direction, right? So this is where we're going to say delta x equals VIX times t plus 1/2 ax t squared. But then you remember what I taught you about ax being 0 and this whole thing 0, and we're left with this, right? But if we want delta x total, then we have to use time total here. VIX was 70.71 meters per second, and time total was that 14.42 seconds. That is seconds. Jeez Louise. All right, let me just write that again. Okay, so we can see then that the seconds are going to cancel, and we're left with whatever that is. So 14.42 times 70.71, which is equal to 1,019.64 meters. And that is my range. Okay, so there we have it. So we went ahead and solved for all four things. I can even 1,019.64. I can even write that up here. It makes you feel better about that. So there, it's all in the same place now. And there's the answer to our questions. So I'll let you complete the rest of them. I think there's 3 more to do, 1 there, and then 2 more down here on your own. But yeah, so I think that if you can see the projectile as looking like this, understand what we talked about here, understand that the x and y direction K formulas are written independent of one another, the motion is studied independently, and that time is the bridge between the two directions, then I think you can solve all these problems and do a good job with them. All right. Anyways, have a good day.